Hey everyone, sorry for the long title. My name is Yiwei. I'm very glad to be here to present our work. This project is supervised by Professor Zhao and Follmer, and we are from Stanford Shape Lab. The development of head-mounted device had largely improved the virtual reality experience and provide users with various ways of interaction with the virtual environment. However, one essential issue of VR is that it lacks haptic feedback, which may hurt the realism that users fear. Researchers have built different types of grounded or ungrounded haptic device. Sensation of grasping, touching, texture can be provided. However, most of those devices is complex and expensive. They are also specific and only certain types of sensation can be provided. On the other hand, researchers also use a physical proxy to provide the haptic feedback. Physical proxy is easier to interact with. They do not need user to wear external device and also arrange in different types of sensation. However, so here the video shows research align the everyday object to the virtual object and use them as a source of haptics. The problem of this approach is that usually shape mismatch exists between the physical and virtual object. So what is the effect when there is shape mismatch? Imagine the user wants to touch two virtual objects shown in slides. The actual physical prop are shapes in red. So when the user go to touch the virtual shape, it will either be blocked by physical prop or move into the object. In VR, we show the effect of shape mismatch for two cases. Firstly, it will cause the user hands float in the air. Secondly, it will make the user finger get into the object. Both of them will create unrealistic feelings. Researchers have developed several actuated physical prop systems which can build different shapes and decrease the mismatch. For example, here we show two of them using swarm robots or 2.5D shape display. However, almost all those actuated physical prop systems require a complex hardware design, and usually they are expensive. Even the state-of-the-art system is still in low resolution, and more complex and expensive system is needed to get a higher resolution. Another drawback of this approach is that the possible type of physical shapes they can render highly depends on the system design. For example, the shape display on the right can only build 2.5D shape, and if we want to build 3D shapes, the whole system needs to be redesigned. Here, on the other hand, we want to use visio-haptic illusion to solve the shape mismatch problem. The research of visual dominance shows that the visual signal usually dominant than other users' feelings. By leveraging this effect, we can retarget the user's touch, which is displacing the user's virtual hand without noticing. The idea of retargeting touch is to warp the 3D space continuously to match the virtual and physical boundaries, even they are different. Then apply retargeting touch according to the spatial warp. We hope it can decrease the feeling of shape mismatch. This retargeting approach is purely software-based and does not need any hardware. Also, it has infinite resolution. What's more, the types of possible shape it can render depends on the physical prop. So the method itself is general and we can use for different scenarios and can be used for augment to different arbitrary passive prop hardware. So previously, researchers developed several retargeting touch methods. For example, in one linear method example, the hand is gradually moved to the virtual position as the user moves their hands away from their body. However, this method can only work for remapping position, not for different shapes. People also develop 2D methods to measure the finger when it is inside the boundary of an object and when the user looks from a certain direction. Also, energy optimization is also introduced for simple 3D space with a plane-like boundary. However, none of them support fully 3D spatial warping for arbitrary complex boundary. So in summary, our approach should support 40 3D spatial continuous retargeting for arbitrary complex boundary. Also, our methods should allow the user to observe their interaction in all directions. We also want our method to be optimization-based so that the best retargeting can be found in some certain evaluation ways. So, what is spatial warping for retargeting? Imagine a rectangle shape left needs to be remapped to the right in the rounded shape. The shape remapping can be represented by a function g. A spatial warp f is a function defined outside the shape to display user finger. One thing need to be mentioned is that in order to displace hand continuously, the function is not only defined on the shape surface, but also in the space outside the shape. Here, we represent this space using omega. And on the outer boundary of this space, partial omega 1, no warp exists, so the function is identical to its original position. On the inner boundary, partial omega 2, which is the surface of the shape, the warp should remap the physical prop to the virtual shape and thus equal to g. So g here is actually a boundary condition for our spatial warp. However, there are still countless mappings satisfying this boundary. In order to find the exact what we want, we introduce two ways to evaluate the mapping. Firstly, we want the mismatch between the two spaces be as small as possible, which is an integration of displacement throughout the space. Secondly, we don't want users to feel big jump when they move their fingers, so we need to maximize the smoothness, which can be represented by the gradients of displacement. Combine those two together using a parameter lambda, we represent the overall optimization goal as a functional of the mapping function. If you are not familiar with the functional, it can actually be seen as a function of function. When lambda is 0, we only care about the smoothness, and when lambda is large, we care more about minimizing the overall mismatch. Using the calculus of variance methods, this functional optimization goal can then be transferred to be a partial differential equation and can be solved numerically. Check our paper for more details about math. Here we show the results solved in 1D. Here we remap a wall at 1.0 to 1.3 when lambda equals 0, which means we care only about the smoothness. Then the solution of our approach in 1D becomes a linear solution. One thing need to be mentioned is that though we can get linear mapping for lambda equals to 0 in 1D, there's no linear solution for 2D or 3D anymore. When we increase lambda and minimize the total displacement more, the map tries to keep the hand in its original position and then rapidly approach the walls. Here we show the 2D result in a video demo. Here, right side is a physical wall and the cursor represents the physical fingertip. Left is a virtual wall and virtual fingertips. We remap a rectangle to be a different orientation and another rectangle to be a circle. From video, it can be seen that whenever the physical hand is touching the boundary, the virtual hand is also touching the virtual boundary in different shapes. When the hand reaches the outer boundary, it always goes back to its original position automatically. Between the shapes, spatial warp can guarantee the hand moves smoothly. For solution shown above, lambda is set to be 0 and there's, like I said, no linear methods in 2D for arbitrary shape anymore. The animation here shows how the hand can be placed by looking up the spatial warp function. Combined with VR HMD, here it shows a 3D solution where we remap a coffee cup to be a teacup. In the debugging mode, the yellow hand is the actual position of hand and white hand is the virtual hand position. The video shows how the hand is displaced in the space surround the object. We can also apply this method to remap larger scale environment. Here we show a large scale example. a plane monitor surface in front of the user is remapped to be a corner, and the table is also remapped to a complex boundary. Notice that when the user moves their hands between those surfaces, the virtual hands does not jump but moves smoothly. With regard to the perception of optimized spatial warp, while the spatial warp can be solved for any boundary conditions, the users may notice it if max mismatch is beyond the just noticeable difference JND for mismatch. The mathematical property of our methods can guarantee that the max mismatch only happens on the boundary, which means if the maximum displacement on the boundary is less than JND, it will be under the JND throughout the space. We also run a user study to test our methods. Here, 3 types of shape remapping are tested. Stretch means shape is changed in 1 dimension, and for this type, we use ellipsoids. Size means changing in 3 dimensions, and for this type, we use cubes. Corner means we change the radius of filter of an edge, and for this type, we use cuboids with a switchable edge. 3 lambda settings are used for maximizing smoothness, minimizing total mismatch, and hybrid. And the max mismatch for all remapping is designed to be less than the JND. For each type of shape remapping, there are 3 shapes parameters, and for each trial, 1 physical prop and 1 virtual prop is chosen. When the user is required to touch and explore the object freely. Since there's 1 for virtual and 1 for physical, so 9 total pairs for each type. After each trial, 3 ratings will be given, and they are hand position mismatch, hand movement mismatch, and shape mismatch. The score scale from 1 to 5, and 1 means match at all, 1 means not match at all, and 5 means match perfectly. Here, the score for position mismatch is shown. Each color represents average rating for different case, and black arrow bars shows the standard error. Blue here means average rating when virtual and physical shapes are the same, and green means when there is mismatch and we use lambda 0 methods. Red is lambda equals 1 methods, and purple is lambda 10 methods. We can see that when lambda equals 0, no significant difference exists between the same shape pairs and different shape pairs for position matching rating. From the result for movement mismatch, we see that rating for all cases are high. It shows that user cannot feel significant movement mismatch. For the shape mismatch perception, lambda equals 0 methods perform not as good as the same shape cases, but lambda equals 0 methods perform significantly better than lambda equals 10 methods. When we look in more detail at the shape perception ratings, we can see that score for different types of shape remapping. The horizontal axis here for each score plot is the physical type we provide to the user, and vertical axis is a virtual type. The rating is the average score for all users. It shows that our retargeting methods perform good for size and scale, but not very good for corner conditions. For the reason, we believe it is because the local haptic cues of the edge that remind the user with the shape. To summarize, maximum smoothness methods minimize users' reported shape mismatch. User did not feel significant finger position and movement mismatch under maximum smoothness condition, which is lambda equals to 0. And for perceived shape mismatch, our methods work well for remapping scale and size, but perform poorly for remapping corners, where local sensation cues exist. For the future works, we firstly want to focus on multi-finger retargeting, which instead of mapping 1 single point, it will remap the whole hand, which involves retargeting multiple points. It will also involve in higher dimension of retargeting, such as position and joint angles. We also want to explore the methods to combine a low-cost haptic device with our retargeting methods for local curvature cubes. Also, for now, we manually set the boundary conditions, which is a one-to-one surface mapping between 2 complex boundaries, but more automatic way is needed for non-convex complex boundary, which ideally need to be both area preserving and curvature preserving. Also, as I mentioned at the beginning part of this presentation, The retargeting touch approach can also be used to augment existing haptic device. Some of you may have seen prior to Abtaki's presentation, who is also from our group, and presented yesterday on how we can apply retargeting touch to the 2.5D shape display to increase its resolution. In her work, only the previous retargeting touch methods are used. And we believe by combining our novel approach, we can help haptic proxy device increase their resolution and decrease the perceived shape mismatch. We also hope the optimization for smoothness and total displacement idea introduced here can also be used as a guide for other touch retargeting design. That's all my presentation. Thanks for your attention, and all questions are welcome. Thank you.
Hi, Gerard Laputte from Carnegie Mellon University. I really appreciate the comprehensiveness of the method that you've put in here. I have a question on whether there's an assumption here that you're also tracking the object in real time. Have you had any, do you have any insights on whether any errors in that tracking would have an effect on the just noticeable difference that you mentioned over here?
Yeah, thanks for your question. That's a very nice question because in our study, we use the OptiTrack, which the error is kind of small. But I think if the error of tracking is large, then our method will not perform very good because then you may get into the object or float your hands in the air. So I think that would be an interesting topic to explore what kind of tracking we need actually for this method. And thank you. Yeah.
Thanks.
Dong Yoon from University of British Columbia. What would be the consequences of the mismatch between perception of your body and apparent visual movement of your body in terms of, for example, maybe perhaps presence, sense of the embodiment, or maybe even sickness?
Yeah, thanks for the question. So basically, for now, our research focuses on small mismatch. And like I said, we guarantee all the mismatch is less than the GND. So actually, also in our research, we show that almost all the users do not notice that. But I think for large-scale remapping, what you said may be an issue. So I think it would be interesting to explore a large-scale effect of methods and whether that will cause the earness of the user. Yeah, thanks.
Thank you.
Very nice work, Eyal Ofik from Microsoft Research. I was wondering if you tried also concave objects and you thought of how it will affect optimization there.
I'm sorry, so concave
Yes. For example, you had a cup there and just touch it from inside and take into account things such as availability of path between the redirection without hitting anything on the way.
So you're saying we may change the type of physical prop?
All your objects you tried were convex.
Yeah. So you're saying concave or, yeah. So I think that, so our methods, yeah, you're right. So now we just focus on the convex situation, but actually, as long as you have like a boundary condition, we can solve it. So for the retargeting touch. And for the concave methods, I think one possible issue is that, maybe we cannot guarantee a one-to-one map in the space, but I think for the simple concave shape, that will work. So I think it would be interesting to do a follow-up, do some example about the concave shapes. Yeah.
Okay, thank you.
Thank you.
Hi, Jianzhe from Carnegie Mellon University. Yes, so it's a very interesting work, and I'm thinking, so currently all the applications, they are all rigid objects. Are you thinking about some soft objects, like in the real world you are playing with a piece of paper, and in the VR world you are playing with maybe silk or rubber or something, and can you implement a mapping between the morphing between the,
Yeah, that's a very good question. So actually, our group have been working on that topic as a follow-up of this project. So basically, we are trying to use the same technology, but try to render different stiffness using physical prop. Yeah.
Thank you.
Thank you.
So that's it for this session, and the next session will start at 4. Thank you.